Take my word for it, Jack. This new automatic temperature control system is basically the same as the conventional air conditioning units you're familiar with. The main difference is in the temperature control system.
You mean the cooling, heating, and air distribution's the same as the ones I've been working on?
That's exactly what I mean, Jack. The heater core is still the heart of the heating system. A water flow valve is still used to control the flow of hot water to the heater core. The cooling or refrigeration part of the automatic temperature control system uses the same kind of evaporator, compressor, condenser, and expansion valve setup as a conventional non-automatic system. Likewise, the air distribution system is essentially the same. One vacuum actuator operates the heat and cooling doors. One handles the defroster doors. And a third vacuum actuator opens the fresh air door.
You mean all of the new units I see here are part of the new automatic temperature control system?
Right, my boy. And Bob here is just the man to explain what those new units are and how they work. Bob, suppose you start with a basic air conditioning system without any of the automatic control units and add one unit at a time until you've assembled a complete automatic temperature control system.
That sounds like a real logical plan to me, Tech. In order to provide automatic temperature control, the system has to know the temperature inside the car and the temperature of the fresh air to be heated or cooled. That's the only way the system can maintain the temperature selected by the driver. An in-car sensor is used to keep track of the temperature inside the car. This is a temperature-sensitive electrical device that lets less current flow when it's cold, more current when it's hot. An ambient sensor, located in the fresh air stream, works the same way, but it reacts to the temperature of the incoming air. The separate electric signals from the in-car sensor and the ambient sensor are sent to an amplifier located inside the control unit assembly. A third electric signal is sent to the amplifier by the thumb wheel potentiometer. This control lets the driver select the temperature level he wants, just like setting the thermostat in your living room. The amplifier reacts to the in-car ambient and potentiometer signals fed into it to produce an electric control signal. This control signal varies depending on whether the car interior needs more heat, less heat, more cooling, or less cooling. In turn, the amplifier signal controls this transducer.
What the heck does a transducer do?
Well, that's a fair enough question, Jack. The transducer takes the electrical signal from the amplifier and changes it into a vacuum signal. Basically, the transducer is a vacuum metering valve that is controlled by the electrical signal from the amplifier. The vacuum output from the transducer is referred to as control vacuum. The part of the automatic temperature control system that operates on control vacuum is called the control vacuum circuit. But I better let Bob explain how it works.
Well, let me give you an example, Jack. If in-car temperature is lower than selected temperature, the transducer supplies relatively high control vacuum. If car temperature is higher than selected, the control vacuum is much lower. Have I lost you yet?
I don't think so, Bob. High vacuum means the system is supposed to supply high heat, or at least warmer air. Low vacuum means the system has to supply low heat, or maybe cooling.
You're right with it, Jack. Now, control vacuum operates a power servo unit in the control unit assembly. The power servo is a combination vacuum and electric switching device. The electric part of the servo replaces the blower speed switch and automatically controls blower speed. Incidentally, in the ATC system, 5 blower speeds are available for cooling and 4 blower speeds when heating is called for. But before I tell you about the blower circuit, I better explain the vacuum side of the servo. The rotary vacuum switch part of the servo provides automatic control of the vacuum actuators that operate the fresh air, heat, and air conditioning doors. For all practical purposes, the vacuum switch part of the servo replaces the AC and the heat buttons of a conventional air conditioner.
Here's an important fact to remember, Jack. Control vacuum controls the power servo, but all of the lines connected to the vacuum switch part of the servo operate on manifold vacuum. In other words, manifold vacuum, not control vacuum, operates the vacuum actuators. This is called slave vacuum.
Does control vacuum control anything besides the power servo?
It sure does, Jack. Control vacuum also affects the water valve. I better explain that next. A vacuum-operated water flow valve is used with this system. The valve is held closed by a spring. Vacuum opens it. The higher the vacuum, the more the valve is opened, and the greater the hot water flow through the heater core. However, the water valve is not controlled by control vacuum alone. Instead, a water valve thermostat located in the discharge airstream modulates manifold vacuum to minimize temperature fluctuations and maintain a fairly constant discharge air temperature in spite of variations in engine coolant pressure and temperature. There are no water connections at the thermostat, only vacuum line connections. One vacuum line is connected to manifold vacuum, one to the water valve diaphragm, and one is a control vacuum line from the transducer. A thermostatic spring in the water valve thermostat reacts to changes in discharge air temperature to regulate manifold vacuum. For example, as the discharge air warms up, the thermostatic spring tends to reduce the vacuum to the water valve. This in turn reduces water flow to the heater core. At the same time, control vacuum is also acting on the vacuum regulator. As a result, manifold vacuum is modulated by both discharge air temperature and control vacuum before it reaches the water valve.
I think you ought to review what we've covered so far, Bob, using the diagrams in the reference book. They show the basic electrical sensing circuit as well as the control vacuum circuit.
Okay, Tech. This drawing represents the control unit assembly and identifies the amplifier, the transducer, and the power servo. On the left side of the power servo is the rotary vacuum switch mechanism, and the electric blower speed switching setup is at the right. Here we've added the in-car sensor, the potentiometer unit, and the ambient sensor connections to the amplifier. Notice that these units are all connected to an ignition circuit terminal in the amplifier so that the electrical part of the control circuit is live when the ignition is on. In this illustration, the vacuum connection to the intake manifold, the control vacuum reservoir, the manifold vacuum line to the transducer, and the control vacuum connection between the transducer and the power servo have been added. Next, the water valve and the water valve thermostat have been added and connected into the control vacuum circuit.
I see how the water valve thermostat is connected to both control vacuum and manifold vacuum, but here's something I'm not sure about. The electrical control units are connected to the ignition circuit, and the vacuum control circuit gets its vacuum from engine vacuum. It seems to me that the control system will always be in operation anytime the engine is running.
You figured that out exactly right, Jack. Matter of fact, the water valve, the heat and cooling doors, and the blower circuit are always adjusted to deliver the temperature selected by the thumb wheel, even when the off button is pushed in. That's why it's normal to hear the vacuum actuators move the air circulation doors even though the system is turned off. Of course, the blower and compressor don't operate because their circuits are also tied into the push-button switch. Now that you've covered the automatic control system, I think it's time to explain the operating circuits. I suggest you explain the compressor clutch circuit first, Bob.
That's a good starting place, Tech. A magnetic compressor clutch is used, just like our other air conditioning clutches. However, in this system, the clutch is engaged when any button except off is pushed, and the outside air temperature is higher than 32 degrees. But let's look at the circuit. The electrical circuit includes a circuit breaker, or a fuse, a vacuum-operated compressor switch, a compressor ambient switch, and the compressor clutch. Pushing any button except the off button sends vacuum to the compressor switch. This closes the switch contacts. That's because the compressor switch is vacuum operated by a manifold vacuum connection controlled by the push button switch. It isn't connected into the control vacuum circuit in any way. Next in the clutch circuit is the compressor ambient switch. It is a temperature-sensitive electric switch, and it stays closed as long as ambient or incoming air temperature is above 32 degrees. At lower temperatures, the switch contacts open. From this clutch control circuit diagram, you can see that the clutch circuit is controlled by the push buttons and is independent of the automatic control circuits.
And that brings us to the halfway point in another session. So, someone better turn the record. The evaporator anti-frost control is also an independent circuit.
You lost me. What do you mean by anti-frost control?
The evaporator anti-frost control system allows the evaporator to provide maximum cooling without danger of freezing moisture that is condensed out on the evaporator fins and tubes.
But how does it work?
Well, frost control starts with an evaporator temperature regulator switch mounted on the front of the evaporator housing. This is an electric switch having a temperature-sensing capillary tube inserted into the fins of the evaporator. The switch contacts close if evaporator temperature goes lower than about 38 degrees. Electrically, the evaporator temperature switch is connected into the clutch circuit at the compressor ambient switch. That means the input circuit to the ETR switch is hot anytime the clutch circuit is hot. The output terminal of the ETR switch is connected to the ETR valve, which is located at the inlet side of the compressor.
ETR valve? What happened to the EPR valve?
On this Auto-Temp system, the evaporator temperature regulator valve replaces the evaporator pressure regulator valve. They both accomplish the same thing. Control refrigerant flow so the evaporator won't get too cold and frost up. The ETR valve is simply a refrigerant flow valve that is closed by a solenoid. The solenoid is controlled by the ETR switch.
Then it must be strictly an opened or closed valve instead of a modulating flow valve.
Right, Jack. We've pretty well covered the compressor control circuits, heater water valve control, the basic sensor and vacuum control circuits. That leaves the blower speed control and vacuum actuator slave circuits.
And what's a slave circuit?
A slave circuit is one that does all the work but doesn't make any of the decisions. The Auto-Temp vacuum control system makes the decisions and controls the power servo. The power servo in turn controls the vacuum actuator and blower speed slave circuits.
And that brings us right back to the power servo. Let's take up the blower speed circuits first. I don't think it's necessary to trace each blower speed circuit. You can use the circuit diagram for that. Instead, I'll explain how the automatic blower speed control works. As we pointed out earlier, the right side of the power servo is simply an electric switching device. The contacts at the upper part of the switch control blower speeds used for cooling. The lower contacts control speeds available for heating. When control vacuum is higher than 12 inches, the system is calling for high heat. So the movable switch contact arm closes a circuit to give the highest blower speed available for heating. If control vacuum drops to about 11 inches, the servo moves the contact arm. This reduces blower speed one step from the highest blower speed available for heating. At about 9 inches of control vacuum, movement of the control arm switches the blower circuit to a still lower speed. When control vacuum drops to about 8 inches, the contact arm moves to the lowest blower speed position. In the meantime, as control vacuum is dropping and reducing blower speed, reduced control vacuum is also reducing water flow through the heater core. In other words, both the temperature of the air and the amount of air delivered tends to decrease as control vacuum decreases. As control vacuum drops from 8 inches to about 2.5 inches, the movable contact arm keeps moving. This movement increases blower speed from low to high in 5 steps.
5 steps? I thought there were only 4 blower speeds.
There are 5 blower speeds for cooling, but only 4 speeds for heating. The highest speed is available for cooling only. The other 4 speeds are the same for heating or cooling. Highest vacuum gives high speed for heating. Lowest vacuum gives even higher speed for cooling.
I've got that straight. Now maybe you could explain what has been happening over on the vacuum switch side of the power servo.
Coming up, Jack. The rotary vacuum switch part of the power servo controls the vacuum slave circuits. These slave circuits control the vacuum actuators that operate the air circulation doors. For example, when the car is calling for heat and control vacuum is in the range between 8 inches and 12 inches, the power servo rotary switch opens the defroster door just enough to let some air bleed up through the defroster outlets. The heater door is opened, the air conditioning doors are closed, and the fresh air door is opened. If it gets too warm in the car, control vacuum drops below 8 inches. The rotary vacuum switch closes the defroster doors, opens the air conditioning doors, and closes the heater door.
And what about the fresh air door?
The fresh air door stays all the way open whenever control vacuum is more than about 3½ inches. At very low control vacuum, the system is calling for maximum cooling, so the system reduces fresh air intake to about 20%. You better tell Jack about that 20% fresh air switch, Bob.
The switch Tech is talking about is called a vacuum transfer switch. It's connected into the vacuum slave circuit, which controls the fresh air door actuator. Here's what the switch does. When the off button is pushed in, the push button control switch sends manifold vacuum to the rod side of the fresh air door actuator. No vacuum is supplied to the vacuum transfer switch. This closes the fresh air door. When any other button is pushed, the push button control switch does not send any vacuum to the vacuum actuator. The rotary switch in the control unit sends slave vacuum through the transfer switch if control vacuum is higher than about 3½ inches. This opens the fresh air door all the way. When control vacuum drops lower than about 3 inches, the slave circuits supply vacuum to only one end of the vacuum transfer switch. The fresh air door starts to open, but as it does, door movement allows a plunger on the end of the transfer switch to move outward. Plunger movement allows a valve in the transfer switch to cut off the vacuum circuit to the vacuum actuator when the fresh air door reaches the 20% fresh air position. Trapped vacuum holds the door in this position.
This door position is used only for maximum cooling. Now, we could go on and explain what happens in the slave circuit for every push-button position and for every heating or cooling requirement. That would take a lot of time, and you couldn't possibly remember all the combinations anyway. Instead, I think we better spend the remaining time covering the blower circuit units that we haven't talked about yet, so you'll know what they are and what they do.
I sure agree with that, Tech. The electrical blower circuit is protected by either a 30-amp circuit breaker or a 20-amp fuse. The sensor circuits, clutch circuit, and evaporator temperature regulator circuit are also protected by the same circuit breaker or a second fuse. But let's follow the blower circuit. Next in the blower circuit is the master switch. It keeps the blower from operating when the engine isn't running. The master switch is controlled by slave circuit vacuum and remains open until engine vacuum reaches about 8 inches. The slave vacuum circuit that operates the blower master switch when the system is calling for heat contains a thermostatic vacuum delay switch.
This delay switch is an integral part of the water valve, but it doesn't control or affect water valve operation in any way. The water valve just happens to be a convenient place to sense engine coolant temperature. There are no electrical connections to the vacuum delay switch. It is a simple vacuum series switch that is controlled by a wax pellet. It shuts off vacuum to the master switch when engine coolant temperature is lower than 125 degrees. When the automatic control system is calling for heat, but the engine coolant is still cold, the vacuum delay switch keeps the blower master switch contacts open. This prevents the blower from delivering a blast of bone-chilling cold air before the engine warms up.
And that leaves only 2 more blower circuit units. A resistance block having 4 resistance elements is used to accomplish blower speed changes. Imperial models have a high blower relay to provide full battery voltage for maximum blower speed.
The reference book explains how the resistance block and the high blower relay fit into the blower circuit. All we have had time to explain is automatic operation when the auto button is pushed. However, if you understand how automatic temperature control works, you won't have any trouble at all understanding how the other push buttons can override part of the automatic control.
I want to thank you, Tech, and you too, Bob. I'm sure that this session, plus the reference book and service manual, will help me service automatic temperature control cars.
And there's still more help coming your way. Next month, we are going to bring you a practical diagnosis and troubleshooting session on automatic temperature control. And why don't all you technicians out there spend a little extra time studying this month's reference book so you'll be ready to make the most of next month's troubleshooting session.